Theory of gravitation and geometry. Let's start the story about gravitational waves with black holes. The idea of black holes was born more than 2 centuries ago. John Michell and Pierre-Simon Laplace wondered what would happen if we accept Newton's ordinary laws and take into account the increase of the second spatial velocity. That is the amount by which a ball or a stone would have to be thrown at the same time. That is from the Earth and never returns. This velocity is calculated using a simple formula. V is equal to the root of 2gm divided by r, where v is the velocity, m is the mass of the body we want to fly, r is its radius, and g is Newton's constant. The formula is easily derived from the balance of kinetic and potential energy of the body. We take this formula and see that, for example, we can increase the mass of the object while maintaining the radius of the object from which we launched the body. Then the critical speed of full flight will increase, or vice versa, while maintaining this mass. Compress this thing where everything flies, and the speed will increase even more. B eventually will reach the speed of light. That is, Michell and Laplace express the simple but important idea that, according to this formula, such an object can be made so heavy or so compact, so small, that its escape velocity will be equal to its escape velocity. Light. A particular revival of the idea of a black hole in its modern sense has arisen within the framework of the general theory of relativity. There, the picture is a little different. In the future, we should have a general theory of relativity, the theory of geometric gravity. You can read about popular theories of gravity in Alexander Petrov's book Gravitation, 2014, published by Century 2 Publishing House. In this theory, massive bodies distort time around them. Usually, spatial distortions are expressed in the following simple way. Imagine a rubber band, such as a rubber band. You place all sorts of things on it. The heavier the object, the more the surface will bend, and therefore create a hole and attract other objects into it. You send some more balls into the airplane and they hit that hole. This is a good image in how it works. Bodies are attracted to each other because they are disturbed by their environment. Let's continue with this analogy. Such a heavy and compact object can be placed in an airplane. It is important to remember that we are dealing with a combination of mass and radius. A heavy but large object will be pushed through a shallow hole of very large radius with little wall curvature, so it would make the surface relatively weak, and a small ball of very high density will deform significantly. Where it lies, the plane will be so compressed that the space region will seem like a doll and nothing will come out of it. This is, without going into detail, the analog of a black hole in the general theory of relativity. We have a certain area. From an outsider's perspective, it's like a hole in an airplane with clearly delineated boundaries. You can get in, but you can't get out. If things fall into such a hole, the hole enlarges. How a real black hole works is a big and complicated question. Theory allows us to construct exotic solutions to the behavior of particles falling over the horizon. In some models, the horizon itself is not visible. For example, you can prevent some particles from hitting the center block. But if we don't add any tricks, everything must come down to the center. We don't know what happens there, because formally many parameters reach infinite values, which means that our physical laws in this area stop working. Here's the problem. Do black holes exist? On the one hand, that's the general theory of relativity, as predicted by today's standard theory of gravity. On the other hand, researchers realize that it is not an accurate theory. It has excellent characteristics and has been tested as thoroughly as possible. But our experimental and observational capabilities are limited. Black holes are a perfect example of the limitations imposed by nature itself. We need a better theory that incorporates the general theory of relativity. Theorists are working on it. But theory alone is not enough. There must be observational evidence of what happens in very strong gravitational fields. Direct proof of the existence of black holes would be very useful. But how do you detect them? If there are holes and they are black, what can be seen there? The only answer that immediately comes to mind is Hawking beams. The theory proposed by Stephen Hawking in 1975 states that black holes should gradually vaporize. However, for real astrophysical, substellar black holes or supermassive black holes, this is a very slow process. In the real situation, their mass increases only due to the interaction of matter and radiation, and the effects of evaporation can be neglected. For a hypothetical primary black hole of small mass, formed at the dawn of the universe, with a primary mass such as an asteroid, the size of the hole would be the size of the primary particle. Evaporation may play an important role today. The Hawkingian process of black hole evaporation is usually represented as follows. Pairs of so-called virtual particles are constantly being created in the vacuum. This is not against anything. An analogy is appropriate here. Buto for a short time takes energy and creates two particles. They disappear, and everything returns. Imagine this semi-criminal situation. You work in a bank. From time to time you withdraw money from the cash register, leaving a bill. You always get it back the next day. Nothing bad has happened. Nobody knows anything. You got it back for a little while. Now imagine that you can't get your money back. For example, some crisis happened, you got the money but you cannot get anything back. Thus, the bank has lost money. To an outside observer, it may appear that the bank's assets are shrinking or evaporating. Even though the bank has more debt income, money is still flowing out of the bank. Back to black holes. Let a pair of particles appear on the horizon of a black hole, and if one falls into the hole, the other flies away. An observer sees the particles flying towards him from the black hole. The only source of energy that can eject these particles is the mass of the black hole. Thus, to the outside observer, the mass begins to decrease. This is a good illustration, but it overlooks some important aspects of Hawking's evaporation. The key point of the original model is the non-stationary nature of the black hole horizon. It is not meant to stand still. For those who want to understand this in detail, we can recommend the booklet On the Birth and Death of Black Holes by Emilia Akhmedova, published by MCNMO 2015. Here we will try to give a very brief description based on an analogy. There is a very interesting phenomenon called Casimir effect. Vacuum is not only filled with virtual particles but also with electromagnetic waves. If you place two conductive plates parallel to each other, they will protect the interior space from electromagnetic waves. Only waves of shorter wavelengths can be between the plates. That is, the energy density of virtual waves between the plates is less than outside. Therefore, there will be a force tending to move the plates. Conversely, if we start moving these plates, it will cause waves to appear. They'll go from virtual to real. Sounds like a round of applause. Now consider a black hole with an unsteady horizon. The horizon divides space into two separate parts. You can go in from the outside, but you can't go back out. The movable horizon allows you to shake hands with one palm. It is such an extraordinary surface that its movement pulls waves and particles out of the vacuum and makes them real. But this requires energy, and it will be extracted from the mass of the black hole. Black hole evaporation is a quantum process. The horizon is very important for it to be curved. The size of a supermassive black hole is large, so the curvature of the horizon is small and the effect is small. Let's not forget that our distant ancestors who lived on an Earth with a radius of about 6,400 kilometers did not notice its curvature. If the radius of the planet had been 10 times smaller, they would not have been mistaken. Therefore, although the hole represents a large mass, it is slowly vaporizing. As the mass decreases, the velocity increases, and it all ends in an explosion. However, until now, black holes have not been observed to vaporize. Let's return to the reality of astrophysical life and remember what kind of black holes we know of. First, there are black holes in stellar masses. This is where a massive star is located. It burns hydrogen into helium, helium into carbon and oxygen, and finally reaches the iron group elements. The burning cannot progress and the core collapses. If this collapse is not stopped by anything, a black hole forms. The typical mass of such an object is 10 times the mass of the Sun. It's a pretty big black hole. It evaporates very slowly. In addition, there's always some debris floating around. And in addition, there's cosmic microwave background radiation. which currently has a temperature of 2.7 degrees Kelvin, which is higher than supermassive black holes. And all of this goes into the black hole, so its mass increases moderately and there is very little vaporization. There are also supermassive black holes in the centers of galaxies. There are two main scenarios for their formation. Either huge clouds of gas fell into the holes at once, which then expanded, or the first stars formed large, 100, 200 solar mass black holes, which later expanded and absorbed matter. What matters to us now is that these holes are slowly turning into vapor, slower than stars because black holes are colder and more massive. That means it's impossible to even see them vaporize. So, in general, black holes are hard to see. Do astrophysicists believe black holes exist? There is a simple practical answer. No one has ever won a Nobel Prize for the discovery of black holes. Hence, there is no definitive endorsement. At the same time, almost all astronomers are willing to assume that there is one, although not with 100% certainty. It is important to note here that we are not talking about black holes of the general theory of relativity, but about a general class of collapsing objects, and a simple equation of state cannot be determined. We do not observe processes inherent to black holes because we always see something around them. Strictly speaking, we should only talk about black hole candidates because we can currently study the behavior of activity around them. For example, we can detect radiation from accretion disks. The most famous and most cited paper written in our country is devoted to such structures. It was published in 1973 by Nikolai Shakura and Rashid Sunyaev. Constructs a model of the flow of matter around black holes. Everything was necessary. It is very popular among scientists. This work for a long time was even the most cited paper in astrophysics. But studies of disks or the motions of stars around supermassive black holes in the centers of galaxies cannot conclusively prove that these are horizontal objects and not surface objects. Perhaps in a few years, the most reliable source of information about black holes will be gravitational waves. Space-time waves. Thus, we describe gravity using geometric theory. Usually, to illustrate its properties, we use the analogy with an elastic surface, which we have already discussed. Let such a rubber band be flat. Now imagine that you are God, and you point your finger at this plane. You have found a surface that goes on top of it. In a sense, these are gravitational waves, but in this case the finger comes from the outside. Now back to reality. The turbulence must actually be caused by something real in the airplane itself. Basically, if you wave your arms, you are emitting gravitational waves because the arms have mass and disturb the environment. You move them, and the cells move in space. But this is a very weak effect. A powerful effect is achieved if you move massive and above all simple compact objects. Because we don't need a heavy body, at this point, we really need to define time. In this case, black holes are ideal. However, the black hole itself is very symmetrical. It's not going to produce anything. We need some asymmetry. Fortunately, the asymmetric processes we need happen in nature. For example, there were two big stars. Both of them exploded as supernova and formed two black holes. Now they're circling each other. Then we have two balls on an elastic plane spinning around a common center of mass. They are sure to create a furor. The waves are falling. When black holes spin in their orbits, they emit gravitational waves. They take up the energy and momentum of orbital motion. Thus, the black holes gradually move closer together. Gravity is arranged in such a way that if energy is extracted from a two-body system, the speed of orbital motion increases as they get closer together. If there are black holes, it will gradually reach the speed of light. Therefore, before merging, each black hole has a large kinetic energy. So we're looking at the extreme case. We take one black hole and throw it into another black hole. This is a unique process where the collision happens at the speed of light. You can't imagine anything else. There seems to be a lot of energy released. It's being released. Just in the form of what? Because black holes don't have a surface. We are not encountering two simple bodies, but two regions of space-time bounded by a horizon. All the massive energy is released in the form of gravitational waves. When two black hole systems merge, a very powerful gravitational wave is created. Such signals should be picked up by the gravitational wave antennas of LIGO and Virgo. This is the most realistic way to discover black holes in the near future. In other words, scientists will kill two birds with one stone. First, the existence of gravitational waves will be directly proven. Currently, we have direct confirmation. Astronomers have observed a binary system, but not two black holes, but two neutron stars. One of them emits like a pulsar, so it looks like a very precise clock sending us a regular signal. And we see a system approaching. And the only reasonable mechanism to explain it all is precisely gravitational waves. The observational data was completely consistent with the ideas of the general theory of relativity. The astronomers won the Nobel Prize in Physics for the discovery and study of the two radio pulsars. These results were then independently verified and confirmed by the observation of nearly a dozen similar systems. Second, if we detect a signal from merging black holes, we will directly detect gravitational waves, thus proving the validity of the geometric approach to gravity, as well as the strongest argument that we have ever correctly understood it. The nature of black holes. Two holes will merge into one. Its horizon will oscillate for some time, and from here a gravitational wave signal can be detected. So the challenges of detecting gravitational waves are considered very promising. Neutron star mergers. The best candidate for being the first systems in which we can detect a gravitational wave signal are merging neutron stars. They are lighter and less compact than black holes. However, we expect the signal to be visible to the LIGO and Virgo facilities in the next couple of years, unless the merger occurs much earlier than large galaxy clusters. Then distant explosions up to 250 megaparsecs can be observed. Neutron star mergers are a natural byproduct of massive double evolution. We observe double radio pulsars and know that most of these systems should merge in less than the lifetime of the galaxy. Calculations show that in a galaxy like ours, mergers occur every few tens of thousands of years. Black holes merge with each other or with neutron stars. One of the first papers to discuss such a merger was a 1977 paper by John Clark and Douglas Erdley. It investigated the fate of neutron stars in the final stages of the process. Important results on fusion were published in 1984 by Sergei Blinnikov and his colleagues. At present, the processes of fusion of compact objects are studied by numerical modeling on the most powerful supercomputers. And questions still remain. Neutron star mergers are a golden phenomenon. Some current models suggest that most of the gold in the universe was formed by this process, including the gold that Nobel metals are made of. A neutron star merges and glows at all wavelengths. It's not just a powerful source of gravitational waves. When plugged in, a lot of energy is released. This material is heated to high temperatures, resulting in a strong neutrino flux, and of course powerful electromagnetic radiation. Merging neutron stars are prime candidates for sources of short gamma-ray bursts on the order of 1 second in duration. Hundreds of such events have been detected over half a century of observations, and all the evidence suggests that no better explanation can be found. The final confirmation will be the simultaneous detection of a gamma-ray burst and a gravitational wave signal. This is likely to happen in the third decade of the century. When they are combined, not only gold is synthesized, but also many new elements, among them radioactive. Therefore, it is possible to see some analog of a supernova, a powerful flash, but only with maximum radiation in the infrared range of the spectrum. Such phenomena are called kilonovae. The name refers to an inflated initial estimate. The flares are expected to be thousands of times brighter than the flares of new stars. Calculations now show that the light is now 100 times brighter than when it was new. So some astronomers joke that it should be renamed a hecton, but the explosion appears to be longer lasting. Observing such lights in the infrared spectrum should tell us the exact coordinates of the light. Observations of gravitational radiation will not be able to give very precise coordinates for a long time yet, even if the number of detectors is increased, and the two in America and one in Europe are joined by installations in India and Japan. This phenomenon could then be better studied by pointing astronomical satellites and the largest telescopes on Earth. Finally, if there was quark matter deep in the compact matter, quark fragments would fly around the nooks and crannies after the merger. Quark matter can exist as very small particles bands. That is, except for compactness, it does not lose its properties. We hope that a special spacecraft for the study of cosmic rays, AMS-02 and its like, will be able to catch errant rays. Or observations will show that nothing is captured, that is, there is no quark matter. By the way, negative search results happen when they are important and provide important new information. How are gravitational waves captured? Actually, how do scientists want to do it? When a gravitational wave passes through an object, it is compressed and stretched. If we have multiple objects, we can see the distance between them change. For example, if you throw a bead into space and it lines up in a perfect circle, the gravitational wave passing through will periodically cause the circle to become an ellipse and back again. Depending on the polarization of the wave, it will appear to us as expanding in one direction and contracting in the other. If we can measure the distance between different beads, we can feel the weak gravitational wave making the beads wobble. First, scientists tried to place metals such as aluminum in billets and see how they would compress and stretch. To do this, piezoelectric sensors were placed on them. Weber was the first to begin such experiments in the late 1960s and continued them for several decades. Detectors of this type are sensitive in a very narrow band of frequencies corresponding to the empty resonance. This is not ideal, as sources may not produce waves in this narrow frequency range. For example, neutron star mergers will change the frequency of the signal, increasing as the objects get closer together and the orbital period decreases. Facilities like Weber's are not sensitive enough for detectors. There must be gravitational waves somewhere very close, such as the merger of two neutron stars in a neighboring galaxy. Ours is even better. Or a very close supernova explosion with a large asymmetry. Weber himself said he was able to detect a signal, for example, from a 1987 supernova in the Large Magellanic Cloud. But this news did not inspire confidence in the scientific community. Even larger designs, such as Allegro in the U.S., Nautilus and Auriga in Italy, cooled at lower temperatures, did not produce any significant results. Therefore, they are now using a different method. Large laser interferometers are now being used. They are sensitive to a very wide range of frequencies. The fitting parameters were chosen based on the properties of the signal expected from the merger of two neutron stars. In many ways, such devices are similar to the famous setup of Albert Michelson and Henry Morley, who proved the existence of the ether. Only modern detectors are larger. Imagine mirrors suspended in a vacuum tunnel several miles apart. When a gravitational wave occurs, they move slightly relative to each other, and you can see it. A laser beam passes between the mirrors, which after reflection hits a detector where the interference is observed. As the mirrors move, the path of the laser beam changes, and therefore the interference pattern changes. This is a very subtle method of measurement. Of course, the mirrors don't rest. They can detect seismic signals, detect heavy trucks traveling dozens of miles away from the observatory. They vibrate because of their limited temperature, that is, because of thermal fluctuations. Finally, even photons from a laser beam are reflected by mirrors. We're talking about such subtle effects. But all these influences can be accounted for or filtered out. Vigomir Braginsky's group from the physics department of Moscow State University made a significant contribution to understanding the nature of noise and methods of dealing with it. And then think about it. Scientists will feel the shoulder of a 2-kilometer-long interferometer change to -18 meters. Not only is it much smaller than an atom, it's much smaller than the nucleus of an atom, but it can be measured. It is hoped that gravitational waves will soon be discovered. In this way, we will not only open a new window on the universe, but we will also have credible evidence for the possibility of black holes. Then it's time for a cosmic kiss. The Space Laser Interferometer project has been in development for decades. The distance between bases with laser installations will reach tens of millions of kilometers. This project is now called ELISA. It was created by the European Space Agency. The launch is scheduled for 2034. Such a detector will be sensitive to the waves of supermassive black holes. They themselves are large, on the order of astronomical units. Consequently, the detector would have to be large because a pair of supermassive black holes at the center of a far-flung galaxy emits gravitational waves with long wavelengths compared to the distance between the holes. Better next-generation space detectors will likely be able to detect fundamental cosmological gravitational waves. Artificial gravitational wave detectors have an interesting competitor: radio pulsars. The periods of these objects can be measured with fantastic accuracy, rivaling Earth's best atomic clocks. This means we can predict when the next pulse will arrive if there is nothing in the way. Gravitational waves distort space, so a signal from a pulsar entering a wave will be delayed, and this can be seen. This idea was first developed by Mikhail Sajin in 1978. Supermassive stars, close pairs of supermassive black holes, mergers of supermassive black holes in various distant galaxies, etc., because space is filled with low-frequency gravitational waves. By observing pulsars for a few tens of milliseconds, one can find correlated changes in their period. These changes are related to the background of the gravitational waves. 3 major projects are currently underway, bringing together radio astronomers from different countries to search for such a signal. Until giant spaceborne laser interferometers become available, this will be the best source of information about low-frequency gravitational waves. Fast stars. Typical star speeds are somewhere between 10, 20, and 30 miles per second. This is faster than their nearest neighbors. In addition, stars rotate around the center of the galaxy. For the Sun, this speed is just over 200 kilometers per second. But as an individual parameter characterizing a given object, its velocity is more important than that of its nearest stars, or if you prefer, of the gas in the interstellar medium. Thus, for neutron stars and black holes, this speed is much higher on average. Why? An object in space has several ways to accelerate. The first and simplest is interaction with another organism. Then the object can pick up speed. That is, it will absorb the energy of the other object. When more than 2 bodies are involved, the interaction becomes more effective. Thus, you can speed up the process very quickly. For example, a new class of sources has recently been discovered: superfast stars. We have already talked about them above. Their speed is very high by stellar standards and can even reach thousands of miles per second. A clear sign of interaction with something large and heavy. Large and heavy objects exist in a single piece of galactic space. At its center is a supermassive black hole. Its mass is about 4 million solar masses. If a pair of stars fly too close to this black hole and are torn apart by the tidal force, one of the stars can reach high velocity and fly away. It could be a regular star, a neutron star, a black hole, or a white dwarf. Dozens of superfast stars are known, but they are all very far away from us. Observations show that they actually fly from the center of the galaxy. They are all simple, usually not very large stars. Neutron stars or black holes with these speeds have not yet been detected. There is another exotic mechanism for creating ultrafast stars. Astronomers observe the most interesting phenomenon of star formation. If a star passes too close to a supermassive black hole, it is torn apart by tidal forces. The resulting gas spirals into the black hole and we see a burst of radiation. If we say that what doesn't kill us makes us stronger, we can say that what doesn't tear us apart makes us faster. If a star is attracted by the tidal force of a supermassive black hole, it can, even if it is alone, pick up extra speed and thus become superfast. And it's quite extraordinary, because it flew away, that is, without looking. Of course, you can't accelerate a compact object. Interconnectivity and acceleration. Neutron stars and black holes are essentially ultrafast. That is, they can be dispersed by a supermassive black hole through a binary explosion. This is a very exotic mechanism. Of course, it doesn't work at solar sites. Around us, if we look at ordinary stars, there's a group of interesting objects called shoot stars. As you can imagine, their speeds are faster than their neighbors. More often 70 kilometers per second, sometimes 100 kilometers per second. How do they achieve that speed? There are two other ways. We've already talked about the first one. It's an interaction with another body and an additional source of energy. Except the other body is not a supermassive black hole. Collective interaction occurs, for example, in a dense cluster of young stars, and some stars lose energy while others slip away and escape. The second method refers to binary systems. If we have two stars orbiting each other, one explodes, meaning it suddenly becomes lighter, and matter flies out of the system, leaving the second star with no gravitational pull. But it had some orbital velocity, and all that orbital velocity will remain. However, the star will slow down a bit as it flies away from its lighter neighbor, but not that much. Hence, if before the collapse the orbital velocity of the double system was 100 kilometers per s, then after the collapse of the system the star could fly away at 70 kilometers per s. Naturally, neutron stars and black holes can also gain speed in this process. They also form as a result of supernova explosions. This is called a simpler effect. Like a stone thrown from a sled, they spin, bend, and then get tossed. Here, a star or black hole is held by gravity, spins, and then flies away by gravity.